Somewhere in the quiet dark, a small blue planet turns beneath a gentle sun. Above it, the universe stretches for billions of light years, a sea of stars, dust, and time. Tonight, we're going to drift through it together, from Earth's thin blue air past the moon and the sun, through the Milky Way and out to the very edge of what can be seen. It's the story of everything, how it began, how it moves, and how it will one day fall silent. So find a comfortable place, let the world slow down, and look up. The universe is waiting, and it has a story to tell.
If you were to step a few hundred kilometers above the ground and look back, you'd see a miracle wrapped in cellophane. From orbit, Earth isn't the vast, endless realm it feels like from the surface. It's a delicate marble, rimmed by the faintest wisp of blue. That shimmer, the atmosphere, is all that stands between every living thing and the vacuum of space. It's an astonishingly thin blanket. If the planet were an apple, the atmosphere would be its skin. Within that paper-thin film is everything we've ever known. Mountains, oceans, cities, wars, love stories, breakfast. And yet somehow it manages to hold an entire climate system in motion. The air itself was a mystery for most of human history. For millennia, people thought it was simply nothing. Then, in the 1770s, Joseph Priestley and Antoine Lavoisier began isolating the gases that make it up. Mostly nitrogen, a healthy dose of oxygen, a splash of argon, and a handful of trace characters like carbon dioxide and methane. Together, they form an invisible soup that makes life possible and, incidentally, paints the sky blue. That color comes courtesy of Lord Rayleigh, who in 1871 worked out that shorter wavelengths of light, blue ones, scatter more easily in air than longer, red ones. Every sunrise and sunset is just sunlight getting bent and diffused by billions of jostling molecules. From ground level, it's lovely. From space, it's practically non-existent, a glowing thread wrapped around a rock. Inside that glowing thread, chaos reigns with surprising grace. Warm air rises, cool air sinks, and the whole atmosphere shuffles itself about like an overexcited lava lamp. The Coriolis effect, named for a French mathematician who probably never imagined weather maps, sets hurricanes spinning and jet streams twisting. NASA's satellites now watch these planetary pirouettes in real time, tracking currents that move heat, water, and dust around the globe like a slow-motion heartbeat. Below the air, the oceans keep the score. They absorb nearly all the excess warmth the sun throws at us, something like 90% of it, and release it politely over centuries. Benjamin Franklin was the first to chart the Gulf Stream. Today, we know it carries more water each second than all the world's rivers combined. Thanks to the ocean's generosity, our winters are bearable and our summers mostly survivable. The ground beneath those oceans is even more restless. In 1912, Alfred Wegener suggested that continents actually move, a notion so radical that most of his peers laughed him out of the room. They stopped laughing half a century later when seafloor mapping confirmed that he was right. The planet's crust is broken into drifting slabs that slowly rearrange the world, creating mountain ranges and earthquakes as they go. It's geology's version of slow jazz, measured, improvised, and occasionally explosive. Far below all that action, 3,000 kilometers down, a swirling ocean of molten iron spins around a solid metal heart. This motion generates the magnetic field first measured by William Gilbert in 1600. Without it, the sun's constant stream of charged particles, the solar wind, would strip the atmosphere away like lint off a jacket. Instead, those particles are diverted toward the poles, where they paint the night with ribbons of green and violet light. The aurora is beautiful, yes, but it's also the planet's way of quietly deflecting death. Everything alive depends on this astonishing balance. James Lovelock and Lynn Margulis, working in the 1970s, described Earth as a self-regulating system, the Gaia hypothesis. It's not mystical, just practical. The biosphere constantly tweaks the air, water, and temperature to keep itself comfortable. Trees exhale oxygen, oceans inhale carbon dioxide, microbes recycle nitrogen. Even the chemistry of clouds participates. If you've ever wondered why the planet hasn't boiled or frozen over more often, it's because life itself refuses to let it. From the ground, the sky feels endless. From orbit, it's heartbreakingly small. When the Apollo 8 astronauts photographed Earthrise in 1968, they gave humanity its first real sense of scale. One fragile orb floating in a sea of black. Since then, every satellite and probe that's looked back has delivered the same humbling message. There is nowhere else even remotely like it. As the sun sets, the atmosphere performs a nightly miracle of physics. The planet, having absorbed sunlight all day, begins to radiate infrared heat back into space. Greenhouse gases, water vapor, carbon dioxide, and methane catch some of that warmth and send it back down again, keeping the surface cozy. Without this effect, first calculated by the Swedish chemist Svante Arrhenius in 1896, Earth would be an ice ball at about -15 degrees Celsius. With too much of it, we get quite the opposite problem. Astonishingly, every detail of this arrangement, the tilt of Earth's axis, the distance from the sun, the thickness of the air, sits just in the right range for liquid water and biological mischief. Change any of them slightly, and you would have a frozen wasteland or a boiling desert. Somehow, we've landed squarely in the middle, on the one world that knows how to make coffee. Even the numbers are oddly comforting. The planet spins once every 23 hours, 56 minutes, creating day and night. It loops around the sun every 365 days, 6 hours, giving us seasons. The sun bathes us in about 1,361 watts of energy per square meter at the top of the atmosphere. Scientists call it the solar constant. Roughly a third bounces back into space. A third is absorbed by clouds and air, and the rest hits the ground to become wind, rain, and photosynthesis. The arithmetic of life is remarkably tidy. Meanwhile, microplankton in the sea are quietly responsible for half the oxygen in your lungs. They've been added for more than 2 billion years, ever since their ancestors triggered the great oxidation event that turned a choking planet into one fit for lungs and leaves. Without them, the oceans would be anoxic sludge, and we'd be a footnote in chemistry. Seen from space, however, all that fuss reduces to a serene glow. The world spins, clouds swirl, lightning flashes within storms so vast they could swallow continents. High above, faint pulses of red light called sprites dance in the upper atmosphere, discovered only in 1989, linking the sky's electricity to the Earth below. Everything is connected, humming along in improbable harmony. Physicist Richard Feynman once remarked that everything that living things do can be understood in terms of the jiggling and wiggling of atoms. If he's right, and he usually was, then the entire Earth is an exquisite piece of choreography, 1 billion trillion atoms jiggling in the shape of forests, whales, clouds, and us. From a few hundred kilometers up, it's difficult to feel important. The continents fade into texture, the oceans gleam like liquid glass, and the thin blue line, that miraculous skin of gas, glows quietly against the black. It holds every song, every word, that every bit of history that ever happened. And so our journey begins here, on the only known island of life in an ocean of space. Above this veil lies the moon, the planets, the sun, and far beyond the vast and star-flecked darkness we're about to enter. For now, let the world turn beneath you. The air is steady, the oceans breathing, and the night coming on. Soon, we'll leave this blue cocoon behind and follow the light out into the deep.
If the Earth is home, the Moon is the porch light, always on, a little cold, and impossibly far away. It sits about 384,000 kilometers from us, which doesn't sound dreadful until you realize that if you could drive there at motorway speed, you'd arrive sometime next spring. Yet for all that distance, it's our closest neighbor, our oldest companion, and the reason oceans heave, calendars exist, and lovers write poetry. The Moon began violently. Roughly 4.5 billion years ago, something the size of Mars, a body scientists call Theia, smacked into the early Earth. It was not a gentle tap. The impact liquefied much of both worlds and flung molten debris into orbit. Within months, that debris gathered itself, like batter swirling into a ball, and cooled into the Moon. Geochemists confirmed the kinship in the 1970s when Apollo samples revealed the same isotopic fingerprint as Earth's crust. We are, quite literally, made of the same rock. One planet and one wayward shard of it circling endlessly. For most of human history, the Moon was a lantern and a mystery. Galileo's crude telescope in 1609 showed that it wasn't a perfect heavenly sphere at all, but scarred and mountainous. His sketches of craters and shadows horrified people who still thought the heavens were divine and smooth. Today, spacecraft have mapped those craters in exquisite detail. 9,000 named features, the largest called South Pole Aitken, a basin big enough to swallow Australia. The Moon's surface tells a story of silence and punishment. With no atmosphere, there is no weather to erase the past. Every meteor that ever struck left its autograph intact. Neil Armstrong's footprints in 1969 are still there and will likely remain for millions of years, preserved better than any museum exhibit on Earth. Despite its stillness, the Moon moves with purpose. As it orbits, it pulls on the Earth's oceans, lifting entire seas by a meter or more. Isaac Newton explained this in 1687 as a simple matter of gravity. The Moon's tug is slightly stronger on the side of Earth facing it and weaker on the far side, creating two bulges that chase the satellite around the globe. The oceans obey like a slow, obedient tide clock. The Sun plays a supporting role. When the Sun and Moon line up, we get especially high spring tides, and when they pull at right angles, we get the modest neat variety. It's celestial teamwork at its most elegant. Those tides have been running far longer than the continents have held their current shapes. They mix nutrients, drive currents, and once may have even coaxed the first creatures onto land. Each retreating wave left pools that demanded sturdier fins and stronger lungs. Without that gentle lunar rhythm, evolution might have taken an entirely different route, perhaps one without beach holidays. The Moon's pull does more than move water. It steadies us. Because of the Moon, Earth's axis tilts at a stable 23.5 degrees. Without that anchor, our planet would wobble chaotically like Mars, whose tilt can swing wildly over eons. A stable tilt means predictable seasons, a quiet gift that allowed forests, migrations, and human agriculture to flourish. When you look at the Moon, you're really looking at the reason strawberries ripen in summer instead of winter. The Moon is also a master of light. It shines not by its own fire, but by borrowed sunlight, reflected from dust as pale as powdered glass. That faint glow is only about 1/8 as bright as daylight, yet it has been enough to guide travelers and timekeepers for tens of thousands of years. Ancient farmers used its phases as a calendar long before anyone invented writing. Even today, the rhythm of waxing and waning still regulates religious festivals, tides, and according to some studies, the sleep cycles of coral and people alike. If you've ever watched the moon rise, you've witnessed a small illusion of physics. Near the horizon, it looks enormous,
a trick of perception rather than optics. Our brains compare it to trees and rooftops and assume it must be huge. High overhead, it seems smaller, though it's no closer or farther away. In truth, the moon's size in the sky is a cosmic coincidence. It's 400 times smaller than the sun, but also 400 times nearer, so the two disks appear almost identical. Because of that, we get the rare perfection of total solar eclipses, moments when the moon slides neatly across the sun and turns day to twilight. The odds of such a match are astronomically slim, and in a few 100 million years, the moon will drift too far away for them to happen at all. Drift is literal. Each year, the moon recedes from us by about 3.8 centimeters, measured precisely by lasers bounced off the reflectors the Apollo 11 and 14 astronauts left behind. That doesn't sound much, but it means the days are gradually lengthening. When dinosaurs ruled, a day was about 23 hours. In another 100 million years, it'll be closer to 25. Time itself, in a small way, is a lunar project. The moon has moods of its own. Its far side, the dark side, though it gets just as much sunlight, remained unseen until 1959, when the Soviet Luna 3 probe sent back the first blurry photographs. It turned out to be a landscape of mountains and craters, rougher and older than the face we know. For all its familiarity, half the moon's story was hidden until a single camera looked the other way. And then there's the human story. The brief but glorious decade when we actually went there. Between 1969 and 1972, 12 men in bulky suits walked its surface, a feat of physics, courage, and paperwork. They left behind flags, experiments, a few family photographs, and roughly 96 bags of assorted waste, proof that wherever humans go, we bring both science and litter. Since then, no one has returned, though a new generation of spacecraft now orbit, map, and dream of going back. Scientists still find surprises. Tiny beads of volcanic glass and Apollo samples show that the moon once erupted fire fountains. Water molecules cling to shadowed craters near the poles, likely deposited by comets or forged by solar radiation. The moon, it seems, is not entirely dead, just sleeping very soundly. When you step outside on a clear night and see it hanging there, you're watching a 4 billion-year conversation between two worlds. The tides rise and fall, the days stretch imperceptibly, continents breathe in time with an object that was once part of themselves. It is easy to forget that the moon isn't shining at us, it's shining with us, a constant reflection of sunlight bouncing between old companions. Soon we'll follow that light farther out, past the orbit of the moon, through the solar wind, toward the heart of the system itself. For now, let it hang above the oceans, tugging gently at their skin, keeping the planet steady as it turns. The porch light is still on, and the road into space is just beginning.
Every life that ever warmed its hands, boiled an egg, or blinked in daylight owes thanks to a small, unassuming star 150 million kilometers away. It's easy to forget that the sun isn't up there in any directional sense. It's out there, a 1.4 million kilometer wide ball of incandescent gas, and we are the ones doing the circling. The ancients, to be fair, can be forgiven for thinking the reverse. When your feet never move but the sky does, you can hardly blame Copernicus for needing courage. The sun contains 99.86% of all the mass in the solar system. Every planet, asteroid, and wandering speck of dust together make up the remainder, the cosmic equivalent of pocket lint. Its diameter could fit 109 Earths side by side, yet it spins once every 27 days with all the poise of a slow pirouette. The Greeks thought it a flaming chariot. 20th century physicists discovered something far stranger and vastly more stable: nuclear fusion. In 1920, the British astronomer Cecilia Payne first suggested that stars were mostly hydrogen, not iron as previously assumed. 20 years later,
Hans Bethe worked out how that hydrogen fuses into helium, a process that converts about 600 million tons of matter into energy every second. That energy streams outward as photons, bouncing around inside the sun for tens of thousands of years before finally escaping into space. 8 minutes and 20 seconds after that, a tiny fraction lands on your nose. It is, by any measure, a very gentle form of apocalypse. Each square meter of Earth at noon receives roughly 1,361 watts of solar power, known romantically as the solar constant. Without it, our world would be a frozen pebble. With too much of it, we'd resemble Venus, proof that moderation, even among stars, is underrated. The sun is not a serene object. Its surface, the photosphere, seethes at about 5,500 degrees Celsius. Dark patches, known as sunspots, first recorded by Galileo in 1610, are slightly cooler regions shaped by tangled magnetic fields. From time to time, those fields snap, launching flares and coronal mass ejections that hurl billions of tons of plasma into space. When one happens to be aimed our way, it can rattle Earth's magnetosphere and paint the polar skies with aurorae. In 1859, a particularly feisty flare, the Carrington event, lit telegraph lines on fire and made the northern lights visible in the Caribbean. It remains the only time the sun literally set technology ablaze. Underneath that fury, the sun hums. Astronomers at Stanford's Helioseismic Observatory listen to it the way doctors listen to a chest. Pressure waves reverberate through the interior, allowing scientists to map regions we can never see. It's a stellar ultrasound, revealing that the core, where fusion occurs, reaches around 15 million degrees Celsius, warm enough that atoms forget their manners entirely and merge into new ones. Energy takes a leisurely route from that core to space. Photons scatter through layers of plasma in a random walk that may last 100,000 years before emerging at the surface. The light touching your window this morning began its journey when Homo erectus was discovering fire. After that, it traversed 150 million kilometers of emptiness in just 8 minutes. It's difficult not to admire such punctuality. All that brilliance won't last forever. Stars are like bank accounts with no deposits. Once the hydrogen runs out, the balance declines rapidly. In roughly 5 billion years, the sun will swell into a red giant, engulf Mercury and Venus, possibly singe Earth to cinders, and then settle into a dense white dwarf ember. Fortunately, that's plenty of notice. Humanity can procrastinate in comfort for several geological epochs. In the meantime, the sun rules a tidy kingdom. Its gravity keeps the planets in obedient orbits described by Kepler 4 centuries ago. The same invisible leash also holds comets, asteroids, and dust in sweeping ellipses that create the faint zodiacal light, sometimes visible before dawn. The entire solar system, in turn, drifts around the Milky Way at about 230 kilometers per second. So while it looks as though the sun stands still, it's really hauling us through space at 800,000 kilometers per hour, a cosmic road trip with no brakes and no destination. Sunlight is the great democratizer. It fuels photosynthesis, drives weather, and powers almost every ecosystem on Earth. Even fossil fuels are simply ancient sunlight in solid form, carbon that once captured photons in the Devonian and has been waiting underground ever since. Every candle, engine, and campfire is a faint echo of that thermonuclear heartbeat in the sky. Yet for all its might, the sun is middle-aged and ordinary. Astronomers classify it as a G-type main sequence star, one of perhaps 200 billion in our galaxy. It is not the biggest, brightest, or hottest. It just happens to be near enough to matter. In cosmic company, it's the quiet neighbor who minds its business and pays the bills on time. Perhaps that ordinariness is its greatest gift. A more temperamental star would have boiled us away or frozen us solid. Instead, ours flickers with reassuring constancy, a dependable hearth at the center of a cold universe. Every dawn, the planet turns its face toward that light again, and every dusk it turns away, storing a little warmth for the night. Now, with the sun behind us, we can begin to drift outward. Ahead lies a family of worlds, each peculiar, each shaped by the same light in different ways. Mercury, with its scorched skin, Venus under its choking clouds, Jupiter rumbling with storms big enough to swallow Earth whole. For the next leg of our journey, we leave the furnace and follow its children, the planets that dance eternally in the sunlight.
The solar system is sometimes described as the sun plus debris. That sounds a bit rude, but it's largely accurate. Out of the original cloud of gas and dust that formed the sun 4.6 billion years ago, almost everything fell into the center and ignited. What remained, less than 0.1%, became the planets, moons, asteroids, comets, and other odds and ends that now whirl obediently around it. We live, in short, in the cosmic leftovers drawer. First out from the sun is Mercury, a burnt marble racing around its parent star every 88 days. It's small, barely bigger than the moon, and made almost entirely of metal. Temperatures there swing from 430 degrees Celsius in daylight to negative 180 degrees Celsius at night, the astronomical equivalent of living inside an oven that occasionally forgets to turn on. Because it spins 3 times for every 2 orbits, a single day on Mercury lasts nearly 2 Earth months. Mariner 10 in the 1970s, and later the Messenger spacecraft, revealed a world hammered by impacts and baked so hard the rocks have cracked from heat stress. There's practically no atmosphere, just a trace of helium and sodium blown in from the solar wind, an environment perfect for robots and nobody else. Next comes Venus, often called Earth's twin in size, but not in temperament. For reasons still debated, its carbon dioxide atmosphere grew so thick, about 90 times heavier than ours, that it created a runaway greenhouse effect. Surface pressure equals standing a kilometer underwater, and temperatures hover around 465 degrees Celsius. Lead would melt, plastic would vaporize, and you would too. When the Soviet Venera 13 lander touched down in 1982, it survived only 127 minutes before the electronics succumbed to the heat. Still, the planet's yellow clouds hide mysteries: slow lightning, high-altitude winds moving faster than any hurricane, and the faint possibility of exotic microbes drifting through the upper haze. Carl Sagan, ever the optimist, once suggested that a kind of aerial life might ride those clouds like balloons, a pleasant thought in a world otherwise better suited to pizza ovens. Then, of course, comes us, the lucky Goldilocks planet, not too hot, not too cold, balanced just right for liquid water. We've already lingered here, but it bears repeating. If you were designing a life support system from scratch, you'd struggle to do better. The exact mix of gases, the right amount of greenhouse warming, and the stabilizing tug of the moon form a combination so precise it seems almost indulgent. Beyond us lies Mars, a place that seems determined to make us hopeful and disappointed in equal measure. It's half Earth's size and once had rivers, lakes, and perhaps oceans. Dried channels photographed by Viking Orbiter 1 in 1976 were the first confirmation that water once flowed there. Today, the planet is an arid rust desert under a wafer-thin atmosphere of carbon dioxide. Average temperature, negative 63 degrees Celsius. But sometimes, in the shelter of craters, frosts still form, and the polar caps grow and shrink with the seasons. Rovers, Spirit, Opportunity, Curiosity, and now Perseverance, have trundled across its plains finding clay minerals that only water could have made. Mars remains the most promising address for life beyond Earth, even if its residents, for now, are all mechanical. Between Mars and Jupiter stretches a region once imagined to hide a missing planet. Instead, telescopes revealed a swarm of rocky leftovers, fragments that never quite assembled. The largest, Ceres, is nearly 1,000 kilometers wide and probably has an icy mantle. NASA's Dawn spacecraft even found bright salt deposits, evidence of briny water once seeping from below. The rest are irregular, tumbling boulders following predictable chaos, cosmic gravel bound together by nothing but gravity's patience. Then comes Jupiter, the monarch of the planets. It's 11 times wider than Earth and more massive than everything else combined. So massive that its gravity slightly distorts the motion of the Sun, making both bodies orbit a common point in space. Jupiter is mostly hydrogen and helium, a failed star that never quite achieved ignition. Its clouds, arranged in belts and zones, roil with storms the size of continents. The Great Red Spot has been raging for at least 350 years, which puts it high on the list of long-term weather events. Beneath the clouds lies a layer of metallic hydrogen, squeezed so tightly it conducts electricity and powers Jupiter's enormous magnetic field. And then there are the moons, 95 known and counting. Io, eternally tortured by Jupiter's gravity, is riddled with volcanoes. Europa hides a global ocean beneath its ice crust, a likely haven for life if anywhere beyond Earth hosts it. Galileo Galilei saw the 4 largest moons through his tiny telescope in 1610. They're still among astronomy's most thrilling sights. Next in line is Saturn, equally grand, but better dressed. Its rings, discovered by Christian Houston in 1655, are made mostly of ice shards, ranging from dust specks to house-sized boulders. They look solid from afar, but are thinner, proportionally, than a sheet of paper. Saturn's moon Enceladus sprays water vapor through geysers at its south pole, hinting at another hidden ocean. Cassini, which orbited Saturn from 2004 to 2017, flew through those plumes and found organic molecules, carbon, hydrogen, nitrogen, oxygen, ingredients for something interesting. Even in the outer darkness, chemistry hums away, quietly, waiting. Farther out lie Uranus and Neptune, the ice giants. Uranus is a peculiar world tilted on its side, possibly the result of an ancient collision that knocked it over. As a result, its seasons last decades. One pole bakes in sunlight while the other end endures a 40-year night. Voyager 2, the only spacecraft ever to visit, found a serene turquoise ball with a surprisingly bland face, though later observations revealed hidden storms in infrared light. Neptune, farther still, is smaller but furier, boasting winds of 2,000 kilometers per hour, the fastest in the solar system. Its moon Triton orbits backwards, a hint that it was captured rather than born there. In the 1840s, 2 mathematicians, Urbain Le Verrier and John Couch Adams, predicted Neptune's existence from tiny irregularities in Uranus's orbit, proving that sometimes you really can find a planet with nothing but paper, pencil, and persistence. Past Neptune begins a realm of ice and mystery, the Kuiper Belt, home to Pluto and countless smaller bodies. Pluto, demoted in 2006 to dwarf planet, took the insult with dignity. When New Horizons arrived in 2015, it revealed a world far more complex than anyone expected. Nitrogen glaciers, blue haze in the sky, and mountains made of water ice. If that's a dwarf, it's a rather majestic one. Farther still, perhaps 2,000 times farther from the Sun than Earth, lies the imagined Oort cloud, a vast sphere of frozen debris. From there, comets occasionally fall sunward, lighting up our skies before disappearing again into the dark. None of this has been seen directly. It's a best guess, stitched from orbital breadcrumbs, but the evidence is persuasive. Altogether, the solar system stretches about 9 billion kilometers from the Sun's warmth to the reach of the solar wind. Voyager 1, launched in 1977, crossed that frontier in 2012, becoming the first human artifact in interstellar space. Even now, it continues to whisper home from 24 billion kilometers away, a faint signal that takes 22 hours to arrive. If you were to shrink the Sun to the size of a beach ball in the middle of a football pitch, Earth would be a peppercorn 25 meters away, Jupiter a marble near the goal line, and Pluto a grain of sand by the car park. The rest would be dust floating on the evening breeze. And beyond the fence, more stars than there are grains of sand on all the beaches of Earth. Our family, then, is modest. 1 star, 8 planets, a few hundred moons, a scattering of comets, and the occasional interstellar visitor like Oumuamua, proof that we have neighbors, though none have stopped for tea. It's a household held together by gravity, running perpetually on sunlight, endlessly circling but never colliding, the perfect celestial mobile. Now, with the planets behind us, we edge toward the limits of home. Out there, past Pluto's shadow, the sun's breath fades, and the long night of interstellar space begins. That is where we'll go next, into the thin darkness where the solar system ends and the galaxy begins.
Every family has a boundary where the neighborhood ends and the countryside begins. For the solar system, that frontier lies somewhere between the orbits of Pluto and the infinite beyond, a vague, misty region where the sun's influence finally gives way to the cold breath of interstellar space. It isn't marked by a signpost or a handy "thanks for visiting" plaque. In truth, no one is entirely sure where home ends and out there begins, but we have a pretty good idea. Just beyond Neptune lies the Kuiper Belt, a sprawling ring of icy worlds left over from the solar system's youth. Gerard Kuiper, a Dutch-American astronomer, predicted its existence in 1951, though he would never see it confirmed. For decades, Pluto seemed alone at the edge. Then in 1992, astronomers found a small icy body orbiting far beyond it, and then another and another. Today we know of thousands. Most are tiny, dark, and frozen stiff, but a few, like Eris, Haumea, and Makemake, are large enough to be called dwarf planets. This distant belt is where comets are born. When their orbits get nudged by Neptune's gravity, some are flung inward, where the sun's warmth wakes them from hibernation. Their ices vaporize, forming bright tails millions of kilometers long. Watching a comet flare in the night sky is, in essence, watching a messenger from the outskirts, an ancient time capsule, briefly illuminated before vanishing again into the dark. The Kuiper Belt is also a museum of history. The objects here are nearly unchanged since the solar system's creation, frozen relics of the same material that built the planets. Scientists study their light spectra to learn what the early solar nebula was made of: ammonia, methane, water, and the occasional organic molecule. It's the cosmic equivalent of finding fossilized leftovers in a very large, very cold fridge. But the real boundary isn't just about rocks, it's about wind. The solar wind. This continuous stream of charged particles flows outward from the sun at about 400 kilometers per second, a gale that fills the entire solar system. It shapes the magnetic fields of planets, lights up their auroras, and defines the invisible bubble we live inside. Astronomers call that bubble the heliosphere. Inside it, the solar wind dominates. Beyond it, the galaxy takes over. The outermost edge, where the solar wind finally slows to a stop against the thin mist of interstellar gas, is called the heliopause. No one can see it, but we've touched it, or at least our machines have. Voyager 1, launched in 1977, crossed the heliopause in August 2012, followed by its twin, Voyager 2, in 2018. When the data arrived, it was like hearing a door close softly behind humanity. The sun's magnetic field faded, cosmic rays spiked, and suddenly the spacecraft were no longer citizens of the solar system. They had gone interstellar. Each Voyager carries a gold-plated record, literally a vinyl record, engraved with sounds and images from Earth. Greetings in 55 languages, the cry of a baby, the sound of surf and thunder, a message from the United Nations, and for reasons best left unexplained, Chuck Berry's Johnny Be Good. The records are expected to last 1 billion years, long after Earth itself has changed beyond recognition. Should some curious being find them, they might wonder why we chose to introduce ourselves with rock and roll. At this distance, the sun is no longer a blazing disk, but the particularly bright star. Light takes more than 5 hours to travel from it to Voyager's antenna. If you could stand on one of those icy Kuiper Belt objects, you would see a black sky filled with sharp stars and one faint golden glow in the distance, home. Far beyond even that lies the realm of speculation, the Oort cloud, named for Jan Oort, a Dutch astronomer who in 1950 proposed that long-period comets must come from an enormous spherical shell surrounding the solar system. No one has seen it directly. It's simply too far away, extending, by some estimates, halfway to the nearest star. The objects out there, if they exist, are frozen remnants from the dawn of time, perturbed now and then by passing stars or the subtle tug of the Milky Way's gravity. When they fall toward the sun, they become the great comets that visit once in 1,000 generations, Halley's, Hale-Bopp, and others that briefly remind us how large our neighborhood truly is. It's a strange thought that our solar system might be 2 light years wide, but it fits. Gravity's reach is endless, though it grows feeble with distance, like a whisper in a gale. The sun's warmth, however, gives up much sooner. At the edge, the temperature hovers only a few degrees above absolute zero. There is no air, no sound, and almost no light. Just the faint pressure of the solar wind dwindling to silence. Voyager 1 now drifts at over 24 billion kilometers from Earth. Its signal, weaker than a watch battery, takes almost a full day to reach us. The spacecraft is old, arthritic, and running on borrowed power, yet it continues to send whispers from the dark. Each time the data arrives, scientists at NASA's Jet Propulsion Laboratory gather quietly around their consoles. What comes through is not an image or a sound, but a pattern of numbers, magnetic fields, particle counts, radiation levels that collectively say, "I'm still here." Someday soon, its plutonium power source will fade, its instruments will fall silent, and Voyager will become a piece of cold, inert metal tumbling between the stars. It will keep moving, forever, through interstellar night. In 1 billion years, it might pass near another star, unnoticed, carrying with it the laughter of children and the sound of rain. Before it left, Voyager 1 turned around for a last look at the solar system. On February 14, 1990, at the suggestion of Carl Sagan, it photographed the solar system from 6 billion kilometers away. Earth appears as a single pixel, a pale blue dot, suspended in a beam of scattered sunlight. Sagan later wrote, "Look again at that dot. That's here. That's home. That's us." It's a simple image, but it captures something profound, how small and improbable our world really is. From this distance, there are no borders, no politics, no noise, just a fragile point of light in an enormous dark. Beyond the heliopause, space stretches unbounded. The sun's dominion ends, and the galaxy begins. Ahead lies the interstellar medium, the quiet dust and gas between the stars, thin as smoke, old as time. That is where our next journey takes us, into the in-between, where no planet circles and no warmth reaches, yet where the seeds of new suns are waiting to ignite.
Beyond the sun's farthest breath lies a darkness so vast it's difficult to describe. It isn't the black emptiness of imagination, but a kind of faintly glowing silence, a place where each cubic centimeter of space contains, on average, 1 atom. Compared with the thick soup of air we breathe, it's practically nothing. And yet, out of that almost nothing, everything is made. The space between stars is not empty. It's a quiet ocean of gas, dust, magnetic fields, and the odd cosmic ray traveling at close to the speed of light. Astronomers call it the interstellar medium, though that makes it sound far more solid than it really is. You could fly through it for 1,000,000 years and never bump into a pebble, but you would pass through entire clouds, vast regions where hydrogen drifts like invisible mist, sometimes so cold that atoms stick together in fragile molecular chains. Those clouds are the raw ingredients of new stars. Within them, gravity gathers atoms together grain by grain until clumps form dense knots called nebulae. When enough material piles up, the pressure in the center ignites nuclear fusion and a star is born. The Orion Nebula, visible even in small telescopes, is one of these stellar nurseries, an immense region 400 light-years wide, glowing from the energy of young suns still wrapped in their dusty cocoons. The light you see from it tonight began its journey when humans were first carving stone tools. The idea that stars formed from collapsing clouds was once considered fanciful. In the early 20th century, many astronomers thought the universe static and eternal. Then, in the 1940s, the Swedish physicist Bengt Strömgren and later the British astrophysicist Fred Hoyle began to show how stars could both be born and die, recycling matter as they went. Carl Sagan would later popularize the thought with a phrase that still sounds quietly miraculous: "We are made of star stuff." The carbon in your bones and the oxygen in your lungs were forged in such furnaces, expelled, scattered, and drawn back together into new forms. You, me, the trees outside the window, all recycled starlight, temporarily arranged. Even between those bright nurseries, space is not as still as it looks. Invisible shock waves ripple through it, caused by ancient supernovae that exploded millions of years ago. Their remnants, spherical shells of gas tens of light years across, still race outward at thousands of kilometers per second, sweeping up dust and triggering fresh rounds of star formation. A single supernova can briefly outshine an entire galaxy, releasing more energy in a few weeks than the Sun will produce in its whole 10-billion-year lifetime. The radiation from these events floods the interstellar medium with heavy elements: iron, calcium, gold, uranium, everything the universe needs for planets, oceans, and toast racks. Each new generation of stars therefore contains a little more metal than the last. Astronomers can even date stars by measuring that metallicity, reading their chemistry like the growth rings of a cosmic tree. In the late 1960s, radio telescopes in the Netherlands picked up faint emissions from molecules adrift in space: formaldehyde, ammonia, even simple alcohols. It was the first evidence that complex chemistry doesn't need planets or laboratories. It can happen in the vacuum between suns. Today, more than 200 different molecules have been identified floating in the dark, including amino acid precursors, the beginnings of life itself. Somewhere in the galaxy, those same molecules are right now gathering on tiny grains of ice, waiting patiently for gravity to do its work again. At intervals, a traveler might pass through a region dense enough to see. The Eagle Nebula, for instance, forms those haunting pillars of creation photographed by the Hubble Space Telescope in 1995. Towering columns of gas and dust, several light years high, eroded into shape by the radiation of nearby stars. They are quite literally the scaffolding of creation, sculpted by light. In images, they look almost solid, like mountains of smoke. In reality, they are thinner than the best vacuum any lab on Earth can make. All this emptiness still manages to hum. Cosmic rays zip through it, magnetic fields twist it into filaments, and stray atoms glow faintly with energy absorbed from distant ultraviolet light. Instruments on Earth detect that glow as a soft radio hiss, the galaxy's background murmur. It's an audible reminder that even in silence, the universe never truly sleeps. Between those threads of gas drift the wanderers, rogue planets flung from their birth systems, orphaned moons, comets frozen solid since before the sun existed. There may be more of them than stars, moving invisibly through the dark. Every now and then one passes within a few light years of us, a nameless traveler, brushing the edge of our bubble before slipping away again. If you could stand somewhere out here, though there's nowhere to stand, you would see the Milky Way stretched across the sky like a luminous river. The stars nearest you would shine steady and white. Those farther away would merge into a soft haze. There is no up or down, no air to carry sound, only a faint pressure from the wind of the galaxy itself.
Time moves differently here, not because of relativity, but because nothing changes quickly. A cloud that takes 1,000,000 years to drift across a star field is considered lively. Astronomers studying this expanse often describe it in almost reverent terms. They speak of circulation, stars forming, living, dying, and returning their matter to the medium that made them. It is, in effect, a galaxy breathing, exhaling dust and light, inhaling darkness and potential. The scale defies imagination, but the principle is simple. Everything that exists is borrowed and someday will be returned. The space between stars is the longest pause in the universe's story, a silence so deep that light itself seems reluctant to cross it. But it is within this quiet that the next act begins. Ahead, faint and sprawling, lies the Milky Way in full, hundreds of billions of suns spinning in an immense spiral of light. From this stillness, we begin to drift toward that shining disk, into the heart of our galaxy.
From a few dozen light-years out, the Milky Way looks like a soft whirl of light hanging in the dark, a glowing spiral roughly 100,000 light-years across, its edges feathered with drifting stars. To the naked eye from Earth, it's a hazy band stretching from horizon to horizon. What you're really seeing is the combined glow of about 200 billion suns, all of them too far away for your eyes to separate. It's like looking into a city from the countryside at night, countless windows blurred into one luminous smear. The name itself comes from the Greeks, who imagined milk spilled across the heavens, Galaxias Kyklos, the Milky Circle. When Galileo first pointed his telescope toward it in 1610, he discovered that the milky haze wasn't vapor at all, but stars by the thousands. It was one of those quietly revolutionary moments when humanity realized the universe was not built to be convenient to our scale. The Milky Way is a barred spiral, a shape confirmed only in the 1990s through infrared mapping by NASA's COBE and later the Spitzer Space Telescope. Its arms are vast tidal waves of gas, dust, and star clusters slowly orbiting a central bar. One complete rotation takes about 230 million years. The last time we completed a lap, dinosaurs had just begun to stretch their necks. The next time we finish one, continents and species will almost certainly be rearranged again. Our own solar system sits about 2/3 of the way out from the center, nestled in a relatively calm lane of space called the Orion Arm, a sort of suburban street between the busier Sagittarius and Perseus arms. Here, things are pleasantly quiet. No dangerous radiation storms, no nearby supernova, just the occasional comet drifting past like a lost balloon. Astronomers sometimes describe this region as the galactic habitable zone, and one suspects we've been rather lucky in our choice of address. The galaxy is not a flat record, but slightly warped, as though someone left it leaning in the heat. It also ripples. In 2018, the Gaia spacecraft measured that the entire disk undulates up and down as it rotates, like the surface of a very slow sea. These waves are probably caused by past collisions, dwarf galaxies passing through, stirring the stars like pebbles dropped in water. The Milky Way is an old structure, still quivering from its many encounters. At its heart sits something we once couldn't imagine. A black hole 4 million times the mass of the Sun, known as Sagittarius A*. It is invisible, of course, but not undetectable. Astronomers track stars whipping around it at thousands of kilometers per second, completing orbits in mere decades. In 2019, the Event Horizon Telescope stitched together radio data from observatories across the world to create a first image of its shadow. A dark circle ringed by fire. It's both terrifying and strangely serene, like a drain in the fabric of space. Around that center swarm stars in every stage of existence. Near the edges are the newcomers, bright, hot blue giants burning their fuel in frantic haste. Deeper in are the old ones, red dwarfs that will outlive the universe itself.
Between them drift globular clusters, spherical collections of ancient suns packed so tightly that from within one, the night sky would never truly go dark. Some of these clusters are nearly as old as the galaxy, fossils of its earliest days. The light that reaches us from all this travel has its own story. Starlight takes tens of thousands of years to cross the Milky Way, and along the way it passes through patches of interstellar dust that absorb blue wavelengths and leave the light reddened. Astronomers call this interstellar reddening, though it's less a color change than a reminder that even light we see is tired from its journey. Every photon that touches your eye tonight began its trip before humanity learned to write. The distances involved are absurd. The nearest major star system, Alpha Centauri, is just 4.37 light-years away, close enough that its light left when the first iPhones were being assembled. Yet, if the Milky Way were reduced to the size of the United States, that nearby star would still be a few dozen kilometers off the coast. The galaxy is so roomy that most stars will never meet another, even if given the lifetime of the cosmos. Despite all that emptiness, the Milky Way is a restless place. Giant molecular clouds collapse into new suns, while older ones die spectacularly, enriching the interstellar medium with heavy elements. Supernovae spark cosmic rays. Neutron stars spin like lighthouses. Magnetic fields twist through the disk like invisible wiring. Seen in ultraviolet, infrared, and radio, the galaxy looks entirely different in each band. A reminder that the visible light our eyes enjoy is only a small slice of its true self. Every now and then, another galaxy wanders too close. The Milky Way has already swallowed several small ones, their remnants strewn around us as faint streams of stars. The next major visitor will be Andromeda, currently 2.5 million light-years away and approaching at a stately 110 kilometers per second. In roughly 4 billion years, the two will merge, producing a single vast elliptical galaxy. If any humans are still watching by then, it should be a rather good show. Our galaxy, for all its splendor, is ordinary, one of perhaps 2 trillion in the observable universe. Each of those other galaxies harbors billions of suns and probably more planets than can be counted. Yet within this ordinariness lies an extraordinary fact. Every atom in your body has spent most of its existence here, circulating through this same spiral of stars, being used and reused in a continuous galactic economy. Iron from an ancient supernova might now be in your blood. A puff of oxygen exhaled by some forgotten red giant may be in your lungs. You are quite literally a piece of the Milky Way that has temporarily learned to notice itself. If you could drift outside the galaxy and look back, you'd see a magnificent swirl suspended in blackness, its arms flecked with pink nebulae and bright clusters. Somewhere in one of those faint lanes, halfway between the center and the edge, a small yellow star spins quietly with a family of planets. On one of them, perhaps at this very moment, someone is lying awake, listening to the slow story of where it all came from. Beyond the outer rim, the starlight fades into the larger web of galaxies that make up the universe itself. Our next step takes us outward, again away from our luminous island of stars, into the immense dark between galaxies where even light must travel millions of years to find another shore.
If the Milky Way were the only island in the sea of night, the universe would still be a marvel. But it isn't, of course. Once you step back far enough to see the whole disk of our galaxy glowing in the dark, you begin to notice others, faint, smudged spirals and ellipses scattered across the black like distant lanterns. Each one is a city of stars, self-contained and dazzlingly far away. The nearest large neighbor is Andromeda, a graceful spiral twice the size of our own and visible to the naked eye on a moonless night if you know where to look. The light you see from it began its journey 2.5 million years ago when early humans were just learning to chip stone into tools. In the telescope, Andromeda looks calm and silvery, but it's moving, heading straight for us. In about 4 billion years, the two galaxies will collide and merge into a single vast elliptical, a cosmic waltz so slow it will take another 2 billion years to finish. The odds of any stars actually hitting are nearly zero. Space, even inside galaxies, is mostly nothing. The stars will simply weave through each other like fireflies passing in the dark. We are not alone even in that. The Milky Way belongs to a small assembly of about 60 galaxies called the Local Group, a kind of suburban cluster adrift at the edge of a much larger structure. Andromeda and the Milky Way are the dominant members. The rest are smaller companions like the Magellan Clouds in the southern sky, irregular little blobs that trail behind us like lost luggage. Around every big galaxy swarm dozens of these dwarfs, each a scattering of a few billion suns, a modest estate by galactic standards. Beyond the Local Group lies the Virgo cluster, a vast congregation of more than 1,000 galaxies bound by gravity but drifting apart through cosmic expansion. The spaces between them are immense, millions of light-years of near-perfect vacuum. On the largest scales, galaxies arrange themselves not randomly, but in filaments and sheets, separated by enormous voids. Astronomers call this the cosmic web, a network so large it defies language. Imagine a spiderweb made of light, stretching for hundreds of millions of light-years, with each intersection a cluster of galaxies. It is, without exaggeration, the architecture of the universe. The first hints of this structure came from Edwin Hubble, who in the 1920s discovered that the nebulae seen through telescopes were not clouds inside our galaxy, but galaxies themselves, and that they were rushing away from us. The farther they were, the faster they fled. That simple observation, now expressed as Hubble's law, revealed that the universe was expanding. Space itself, not just the things in it, was stretching. If you run that process backward, you end up at a moment of compression, the Big Bang, the instant when the entire observable universe was smaller than an atom. Today, we know the expansion is not slowing down, but speeding up, driven by something mysterious called dark energy. It accounts for about 70% of the cosmos, yet no one knows what it is. It doesn't shine, absorb, or interact. It simply pushes. The remaining 30% consists mostly of dark matter, an equally mysterious substance that reveals itself only through gravity. We can see galaxies rotate faster than their visible mass allows, implying halos of invisible matter surrounding them. In total, all the stars, planets, and people make up less than 5% of everything. It's a humbling thought. Almost all of existence is made of things we can't see and don't understand. Astronomers have learned to map the invisible by its influence. In 2013, the European Space Agency's Planck satellite produced the most detailed map yet of the cosmic microwave background, the faint afterglow of the Big Bang, now cooled to just 2.7 degrees above absolute zero. Those subtle ripples in temperature, differences of only a few millionths of a degree, are the fingerprints of the first structures in the universe. Every galaxy, every star, every one of us ultimately traces back to those tiny quantum fluctuations frozen into light nearly 14 billion years ago. On timescales far longer than our species can comprehend, galaxies themselves are transient. They collide, merge, grow, and fade. Stars burn out. Black holes consume what's near them. Supernovae enrich the surrounding gas, which then collapses into new stars. The cycle goes on endlessly, the universe recycling itself on scales of hundreds of millions of years. Even light, which seems eternal, will someday fade to infrared whispers as space expands and stretches its wavelengths thinner and thinner. From our small perspective, it is impossible to truly grasp the scale of all this. The light from the edge of the observable universe has traveled for 13.8 billion years. That means when we look outward, we are also looking backward in time, a kind of cosmic archaeology where each layer of distance reveals an earlier chapter of existence. The most powerful telescopes now peer so far that they see galaxies as they appeared only a few 100 million years after the Big Bang, glowing pink with the first generation of stars. Beyond that, there may be more, perhaps infinitely more, but light from those regions has not yet had time to reach us. To picture this expansion, imagine dots on a balloon. As the balloon inflates, each dot moves away from the others, though none are at the center. The same happens with galaxies. Every one sees itself as the middle of creation. When people ask where the center of the universe is, the answer is simple and slightly disorienting: everywhere. In 1995, the Hubble Space Telescope performed a small miracle. Astronomers pointed it at a patch of sky so empty it contained almost nothing visible, an area the size of a grain of sand held at arm's length. They left the shutter open for 10 days. When the images came back, that tiny blank spot was filled with thousands of galaxies, each containing billions of stars. Multiply that patch across the entire sky, and you get at least 2 trillion galaxies in the observable universe. 2 trillion islands of light, each with perhaps its own version of us, wondering who else is out there. It's almost impossible to process numbers that large. If you could count one galaxy per second, you'd need more than 60,000 years just to get through the visible ones. Yet all of it, from the smallest atom to the grandest cluster, obeys the same simple laws of physics: gravity, electromagnetism, nuclear fusion, entropy. The universe may be incomprehensibly vast, but it is not chaotic. It runs on elegance. Out here, far from the comforting familiarity of the Milky Way, you can finally sense the true scale of the cosmos. The spaces between galaxies are wider than thought allows, yet everything remains connected by gravity, stretched by expansion, and illuminated by the same kind of light that warms our mornings. The galaxies drift apart, but they do so together, carried on the same cosmic tide. Somewhere amid those 2 trillion islands lies the faint dot we call home, invisible from here, but still glowing softly with life and radio chatter, orbiting a middling star halfway down an ordinary spiral arm. The universe is expanding, but for now, at least, we are still in it, a brief, bright flicker on the edge of eternity. At some point, when you travel outward far enough, light itself begins to run out. It isn't that the universe ends. There's no wall, no boundary, no sign reading, "Thank you for visiting creation." But there is a limit to what we can see. That limit is set by time, the age of the universe, 13.8 billion years. Anything farther away simply hasn't had enough time to send its light to us. Beyond that horizon, there may be countless galaxies, maybe infinite space, but they are forever hidden behind the speed of light and the ticking of cosmic time. This limit defines what we call the observable universe, a sphere centered on wherever you happen to be standing. Every observer anywhere in space would have their own, because everywhere is the center from its own point of view. From Earth, the radius of that sphere is about 46 billion light-years, much larger than 13.8 billion, because space itself has stretched during the journey of the light. What we see now are ancient versions of those distant galaxies, caught in a moment long gone. The light reaching our telescopes tonight may have begun its voyage when the first stars were just igniting. In the 1960s, 2 radio engineers, Arno Penzias and Robert Wilson, were testing an antenna in New Jersey when they discovered an odd background hiss they couldn't get rid of. They thought it might be pigeon droppings inside the equipment. It turned out to be the oldest light in existence, the cosmic microwave background, the afterglow of the Big Bang, still humming gently across the entire sky. That faint signal, now stretched into microwaves by 14 billion years of expansion, is our earliest photograph of the universe, a baby picture of everything. Later satellites, COBE in 1989, WMAP in 2001, and Planck in 2009, refine that image into astonishing detail. The glow is almost perfectly uniform, varying by less than 1 part in 100,000. But those tiny irregularities are crucial. They are the seeds from which all structure grew. The brighter specks mark regions that were slightly denser, where gravity could gather matter into the first stars and galaxies. Without those minute ripples, the universe would still be a smooth, dark soup, featureless and lifeless. When you look back to that time, just 380,000 years after the Big Bang, the cosmos was not yet transparent. Earlier still, it was a hot plasma, opaque to light, a roiling fog of particles and radiation. Only when it cooled enough for atoms to form did light escape and begin its long journey. That escaping radiation is what we still detect today, a whisper from a time before there were planets, or stars, or even darkness as we know it. Modern telescopes, like the James Webb Telescope, now probe just beyond the first galaxies, into a period called the Cosmic Dawn. There, we see faint red smudges that are actually ancient galaxies forming less than 500 million years after the beginning. Their light has been stretched by expansion into the infrared, making them nearly invisible until now. Each new detection is a glimpse of the universe trying to switch on the lights for the first time. The edge of visibility is not a sharp line, but a fade into obscurity. Beyond a certain distance, light becomes too redshifted, too weak, too smeared by time to detect. The photons still travel, but the space between galaxies is expanding faster than they can cross. In effect, there are places receding from us faster than light. Not because they are moving through space that quickly, but because space itself is stretching in all directions. Those regions will never be observable, not even in principle. They are beyond the cosmic horizon, outside the reach of causality, like pages from a book we can never open. Physicists have wondered what might lie out there. Some propose that our entire universe, the sum of everything we can see, is just one bubble in a vast multiverse, a cosmic foam of inflating regions forever budding new universes. Others think space might curve back on itself, finite yet unbounded, like the surface of a sphere where traveling straight long enough would eventually bring you home. The truth, for now, is unknowable. The observable universe isn't the universe itself. It's merely the small patch we can illuminate before darkness swallows the rest. And that darkness is growing. Because of dark energy, the expansion of space is accelerating. Galaxies that are now barely visible will someday slip beyond our horizon, their light stretched into invisibility. In tens of billions of years, only the closest galaxies, those bound to ours by gravity, will remain visible. The rest will vanish from view, leaving future astronomers adrift in apparent emptiness, unaware that anything else ever existed. The cosmos will seem to have gone dark, though it is only receding beyond sight. It's a strange fate for such a luminous universe. Every galaxy you see tonight, every point of light captured by a telescope, is part of a temporary show, an epoch in which stars are still being born and light has still time to travel. The night sky we know is not eternal. It's a passing season in the life of creation. But even as horizons fade, the story remains. The atoms in your body, the warmth of the sun, the glow of distant galaxies, all are part of a continuum that began in that early fire. The universe has been expanding for nearly 14 billion years, and for a tiny fraction of that time, it has included eyes capable of noticing. We are the brief awareness of an immense, patient cosmos, and in our noticing, it becomes a little less alone. From this farthest edge, there is nothing left to see but the idea of infinity. Beyond the last galaxies lies the unknown, perhaps more universes,
perhaps nothing at all. What we call the edge is really the limit of our own understanding, a horizon not of space, but of imagination. Everything beyond is possibility. And somewhere in all that possibility, a small blue planet continues to circle its ordinary star, quietly turning, warmed by ancient light. The journey outward ends here, at the boundary of the knowable universe. Beyond this, only silence and the promise that there will always be more to learn.
Everything you've ever seen, felt, or imagined began as a flash of unimaginable brightness. 13.8 billion years ago, there was no space, no time, no before. Then, in a moment smaller than a moment, the universe appeared, hot, dense, expanding, and astonishingly uniform. It didn't explode into space. It created space, carrying every future galaxy and grain of dust outward in its swelling fabric. For the first fraction of a second, temperatures were so high that matter couldn't exist, only energy. Quarks and electrons flickered in and out of being. When things cooled enough for protons and neutrons to form, the universe was barely a minute old. In the next few minutes, those particles fused into hydrogen, helium, and a trace of lithium, the lightest elements, still the most common today. Everything heavier, carbon, oxygen, iron, gold, would have to wait for stars. By the time the universe was a few 100,000 years old, it had cooled enough for atoms to form. The fog cleared, light escaped, and the cosmic microwave background began its long journey. The same whisper Arno Penzias and Robert Wilson stumbled on with their antenna in New Jersey billions of years later. After that came the long dark, hundreds of millions of years with no stars, only drifting hydrogen. Then gravity began to tug, clouds collapsed, and the first suns ignited. The cosmic dawn had arrived. For billions of years since, everything has been a slow elaboration of that beginning. Hydrogen became stars, stars forged heavier elements, and when they died, they scattered those elements across the galaxy. Out of that dust came planets, oceans, trees, and eventually things that could look back and ask how it happened. As the astronomer Martin Rees once said, "We are the ashes of long-dead stars looking at themselves with wonder." The story of the universe is also the story of entropy, the steady drift from order toward disorder. Stars burn fuel, galaxies spread, heat disperses. Energy never vanishes, but it becomes less useful, more diffuse. The second law of thermodynamics, that quiet accountant of existence, ensures that every flame, every thought, every heartbeat leaves a small trail of disorder behind it. The universe has been growing more complicated on the surface while becoming simpler underneath, like an elaborate sandcastle made from the slow collapse of a single wave. Far ahead, the sun will run out of fuel. In about 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, perhaps brushing Earth to cinders. Then it will shrink to a white dwarf, glowing faintly for another few trillion years before fading to black. By then, the Milky Way and Andromeda will have merged into a vast elliptical galaxy, their stars dancing in slow, collisionless embrace. New suns will still form for a while, but the supply of raw gas will dwindle. One by one, the lights will begin to go out. In 100 trillion years, the last stars will flicker and die, leaving only degenerate embers, white dwarfs, neutron stars, and black holes drifting in darkness. Gravity will still be at work, pulling those remnants into quiet orbits, occasionally causing one to spiral into another and release a final flash of energy. Then, perhaps after 10 to 100 years, a number so large it defeats imagination, even the black holes will evaporate through Hawking radiation, releasing their stored energy as faint bursts of light. The universe will become a thin, uniform haze of cold particles. No stars, no heat, no memory, a perfectly even nothing. Physicists call it the heat death, though it will neither be hot nor, strictly speaking, dead. Just complete. Yet even that is not quite an ending. Quantum physics suggests that fluctuations might someday seed new expansions, little baby universes budding off from the old. The cosmos may never stop, only change its form, passing the spark onward in ways we can barely conceive. If so, creation is not an event, but a habit. It's tempting to find this melancholy, a universe rushing towards silence, but it is also extraordinary that any of it happened at all. Against impossible odds, matter arranged itself into stars and planets, then into molecules that could replicate, and eventually into minds that could ponder their own impermanence. Out of physics came chemistry, out of chemistry came biology, and out of biology came awareness, a self-observing loop of stardust that briefly knew it was alive. Every second, about 10 million tons of sunlight fall on Earth. Some of it warms your skin, some feeds the leaves outside your window, and a tiny fraction enters your eyes carrying photons that began in the heart of a star 8 minutes ago. Those same laws of motion and energy govern the galaxies at the edge of time. The same constants shape atoms, stars, and thought. Everything, everywhere, follows the same simple choreography. So perhaps there's comfort in that. The universe may end in darkness, but for a while it glows, and in that glow there is meaning. We are here at precisely the moment when the sky is alive with stars, when galaxies are near enough to see, when light can still cross the gulf. In the unimaginably long history of everything, this is the bright middle act, and we are lucky to witness it. Someday the last photon will fade into the cold and time will lose its purpose. But tonight the stars are still burning. The Milky Way still arches across the sky. The same light that began at the dawn of everything still warms our world, and for now that is enough. The universe began in brilliance, and it will end in quiet. Between the two lies the brief interval we call existence, a momentary bloom of order in an endless sea of possibility. And as that moment drifts towards sleep, perhaps the only fitting thing to do is what the universe itself will one day do: grow still, grow silent, and let the light gently fade.
And so, our journey ends. Not with a bang or a boundary, but with a slow drift back towards stillness. We've traveled from the thin blue veil of Earth through the quiet seas of the solar system, past the frozen edge of sunlight, across the spaces between stars, and out to the very rim of the observable universe. Everywhere we looked, from the smallest atom to the largest galaxy cluster, we found the same astonishing rule: everything is connected. Everything changes, and everything continues. The light that left the first star still moves through the dark. The atoms that once burned in ancient suns now rest in our bones. And somewhere, in a corner of the Milky Way, a small planet turns beneath a yellow star, carrying minds curious enough to notice it all. Perhaps that, more than anything, is the universe's great accomplishment. Not its scale or its age, but its brief moment of awareness. For a little while, the cosmos can see itself and wonder. As you let your eyes close, imagine that long, slow drift, Earth beneath, stars above, galaxies stretched like distant lanterns. The light of all creation still arriving, still traveling, still touching everything it passes. The story never truly ends. It only changes form. And somewhere, in all that vastness, the next spark is already beginning. The universe is still unfolding, quietly, beautifully, endlessly.